through a quick video discussion explanation with regards to the next section of this topic, which is the equilibrium constant. So it's a calculation section essentially, but I wanted to run through a bit of what's each part represents before we look at one simple worked example and a discussion about what would happen with that. And there's plenty of worked examples in the textbook that I'm going to ask you to, or point you in the direction of, to do some reading through on that yourself and then giving it an attempt today. But just to give us a bit of background, so with regards to equilibrium, we've had a discussion about that, and we've talked about equilibrium in the last few days based around certain conditions. So if the temperature of a reaction changes, it means it pushes it one way or the other, or if I increase or decrease the pressure, it changes the equilibrium of a specific reaction. So that's talking about conditions really, but now we're going to look at what the idea is with regards to a mathematical representation or a numerical value that has some kind of relationship to what the equilibrium in a reaction means. So based on the previous Le Chatelier's principle experiment that you looked at for me last week, you can see that if the temperature is kept constant, that we have a specific relationship between reactants and products, and we can put a mathematical value on that. The idea is that in that experiment specifically, if we cooled it down, the reaction went one way. If we heated it up, the reaction went a different way. So if I keep a constant temperature, that means that I can look at the concentration in detail, or I can look at the volume of products or the volume of reactants in detail, and I can look at the mathematics between those things, because one thing is kept the same, the temperature in this case. So that's what happens here when we're talking about equilibrium and the equilibrium constant. We talk about it at a specific temperature. So if that's staying the same, then the things that can change are the amount of reactants that we have, or the amount of product that we have in terms of moles, in terms of volume. Generally, that's what we discuss. Okay, so you can see the formula there, and how that ties in. So it's small a, big A, small b, small c, small d, big D. Lowercase letters represent the number of moles. So you know when we're doing any kind of chemical formula, if you write 2CO2, for example, we know that we've got 2 moles of that. Okay, so the lowercase letters represent the number of moles as mentioned there, and the uppercase letters or the capital letters represent the reactants and the products. So if you can imagine that looks A, the 2 is representing the number of the moles, and the CO2 is represented by the capital A, just to give you a quick example of what that could be. Okay, so the equation is given there. I'll rewrite it just so you can see it even more clearly. Is equal to C D over A B. So we can see that there, and that's the way it's written on the page as well. What I'll suggest is, look, there's good notes here that I've written on the 2 slides that I'm going to show you. If you want to pause it, you want to screenshot it, you want to rewrite these notes yourself, of course, go for it. Okay, it's going to be there for you to use. But just a little bit of info then about what's happening in that equation. We can see the Kc is the equilibrium constant. Okay, so the K represents the equilibrium constant, and C is a concentration. Okay, so we're talking about a specific concentration based around what a calculation question will ask us, because we have specific concentrations of these things based around what's happening here. Okay, so you can see square brackets, as I mentioned. The square brackets I use to denote concentration. So when I use the square brackets, and we're going to use this in the next topic when we have to look at pH as well, you're looking at concentration of reactants, and we're talking about it in terms of moles per liter. Okay, so that's the unit that we use. So if we're not given that unit, we have to do conversions first, but you guys are well used to doing those using your molecular mass and so on. So our tips for using this, as I've written here: 1, the products are always on the top. So if you look at an equation like I have written out here, AA, BB, CC, DD, CC and DD are the products. So they're the ones that are on the top of the equation. The reactants are the ones underneath. So the ones on the right go on top, the ones on the left go underneath. Simple enough. Our concentrations are always multiplied. So again, you can put a little multiplication in there if you so wish. Generally, when we're writing it out, we don't put them in, but if you want to and it helps you, of course, go for it. And then finally, our concentration is raised to the power of the coefficient, which is the lowercase letter. So the coefficient just represents that number that's in front of whatever product or reactant that we're talking about. So, as I said, in the example that I gave you at the very top here, we've got 2CO2. So you can imagine if 2CO2 was in this formula that we were using, that would be the A part in this equation, and that would go in the bottom left. So we would talk about whatever the concentration of CO2 is, and that would be to the power of 2, because I've got 2 CO2s. Okay, so the number that's in front of the reactant, or the number that's in front of the product, goes as the power in the equation. We'll see it in action in the next slide. So the example that I've done is a really simple one, and the simplest one there, okay, which is on page 275 of your textbook. The reason that I picked this one is because I wanted to discuss a little bit further on the detail and the kind of practical implications of what's happening in the mathematics, and then you'll hopefully be able to understand that a bit better and apply it to the next question coming up, or the next ones that you attempt later on. So we've got production of ammonia in our equation here, so similar to the Haber process that you looked at the last day. It's telling me everything that I need to know. It's telling me that the temperature is constant. It's telling me that it's in a 1 litre container, which is quite important as well. And it tells me how many moles of each thing I have. So I've got 13.6 moles of nitrogen gas, 1 mole of hydrogen gas, and 1.5 moles of ammonia. They're all in a 1 litre container. It tells me that. It tells me that in the question. So I've got that number is the amount of moles per litre I have. So I don't have to do any calculation in that. So just to recap, as you said there, if I've got 13.6 moles in 1 litre, so that means I've got 13.6 moles per litre. And the same for the hydrogen is 1 mole per litre of hydrogen, and the ammonia is 1.5 moles per litre. So I have everything there. All of the maths is done for me in this case, because I don't have to do any kind of conversions. If you can imagine, if it told me that they were in a 500 ml container, or a 500 centimetre cubed I should say, I'd have to double all those values, because there'd be that many moles in this much, so there'd be twice as much in a litre. So you have to keep that in mind as well. But in this case we didn't have to do it. So our calculation is done, nice and simple. I've got my product on top, because that's on the right hand side, so that's the thing that's gone on top. And you can see that I'll do it again here. You can see I've got concentration of NH3 to the power of 2, because there's 2 of them in the chemical formula at the very top of the page, all over the concentration of nitrogen multiplied by the concentration of hydrogen, and the hydrogen is to the power of 3 because there were 3 of them in the question, or in the equation at the very start. So all you got to do then is pop in the values. You can see that's 1.5 squared all over the 13.6 by 1, and that's cubed, and then you just pump that into your calculator and you get a value, and in this case we got a value of 0.165. And the important part that I wanted to touch on, you can see, and you can read through all of these, the concentration of ammonia is low compared to the other two. You can see there's 1.5 moles of ammonia and there's 13.6 moles of nitrogen. So there's a small amount of ammonia compared to the amount of the other two. Because that concentration is low, that's the numerator in the fraction. you can see that's the thing on top of the line. That in turn gives us a small number value at the end. You can imagine if I have 100 over 10, it gives me a value of 10. But if I've got 1 over 10, it gives me a value of 0.1. The numerator dictates how big the actual value of the answer is. So if I've got a small number on top, it means I'm going to have a small Kc value or a small equilibrium constant value. With that number being low, it means that the equation is pushing to the left to a certain extent. Okay, if the reaction is pushing to the right, as I've mentioned here, if the reaction is pushing to the right, it means that the concentration of the product is high, and that will then in turn give us a high Kc value or a high equilibrium constant value. And the temperature, the next part, is given because the equilibrium constant is temperature dependent. You can imagine. It tells me that it's at 450. If I change that temperature to 300, or if I change that temperature to 600, it would have an effect on the way the reaction happens. In this particular example, in the production of ammonia, a high temperature will give us a lower equilibrium constant. So when I drop the temperature, and there's a couple of examples in the textbook, it goes to this example specifically, but it says like at 300 degrees there'll be such and such of a equilibrium constant. At 800 degrees it'll be a lower. So it tells you through that, so you can have a look back yourself. So that's that with regards to temperature. The pressure and the volume balance out, okay? So which means that it doesn't change the equilibrium constant value. You know that if I increase the pressure, I decrease the volume, and vice versa. If I increase the volume, I'm decreasing the pressure. So those things balance out evenly. And remember, we're keeping the temperature constant. So if I keep the temperature constant and one of those goes up and the other one goes down, that means that they're moving in tandem with each other. And as one goes up, the other goes down, and vice versa. We talk about that being inversely proportional. But they cancel each other out essentially, because as one goes up, the other goes down, and it's the same as if it was the other way around, and it doesn't really matter. So the only thing that's affecting the Kc, or the equilibrium constant value, is the temperature in this case. Okay, part 4 then, the equilibrium values are equation dependent. So you can see I've got the same products and reactants in these two formulae. Now again, I've just made this one up nice and simple because you've used water in lots and lots of instances. I've got 2 different ways of making it, you can see, and I've got 2 different amounts of each thing. Those equilibrium constant values would not be the same. As you can see, I've written that they're not equal to one another, and the reason for that is because I've got different concentrations of each thing. Nice and simple. Okay, finally, last 2 bits there. The forward and backward equations have different values. So if we look at this one specifically that we were talking about today, if I go that way in my reaction, it has an equilibrium constant value of this 0.165 that we figured out. If I'm talking about it going in the opposite direction, if I am talking about the decomposition of nitrogen to give me a decomposition of ammonia to give me nitrogen and hydrogen, I'd have a different equilibrium constant value. And then finally, the equilibrium constant value doesn't give any indication to the reaction. It's telling me in what direction the reaction is moving, but it doesn't tell me how fast that's happening at all. Okay, so that's a different thing altogether. So that's everything on that. What I ask, would you be able to do a couple of those calculation questions based on the information I've given you here? As I said, pause it, go back, screenshot, do whatever you need to do. Keep these notes if you so wish, and hopefully you'll be able to do a couple of the calculation problems from there. Thank you very much.